Good morning, friends. Welcome to the course of energy conservation and waste heat recovery. Once again, today we are going to see some examples or some of the principles of thermodynamics through example. So far, if you remember, we have learned steam power plant, which is based on Rankine cycle and variation of Rankine cycle. But all the processes we have considered, they are ideal processes. In practice, there will be non-ideal processes, and during non-ideal processes there will be irreversibilities. This has got a very pronounced effect on the performance of Rankine cycle or a steam power plant. So, first we will start with a power plant which operates on a simple Rankine cycle, but it has got some sort of irreversibility. So, I have taken this problem from the source which I have acknowledged here, and let me read out the problem. A power plant operates on a simple Rankine cycle producing a net power of 100 megawatt. The turbine inlet conditions are 15 megapascal and 600 degree Celsius, and the condenser pressure is 10 kilopascal. If the turbine and pump each have an isentropic efficiency of 85% and there is a 5% pressure drop in the boiler, determine A, the thermal efficiency, B, the mass flow rate of steam in kg per hour, and C, the back work ratio. So, let us see how we can proceed with this problem. So, here I have shown a TS diagram of the working cycle, which is very conventional for Rankine cycle, and in the TS diagram what we can see, this is the condition of the steam at the entry of the turbine, that is 1, that is state we have denoted this state as 1. So, from there, if ideal expansion or isentropic expansion is there, then it reaches to 2, but the expansion is non-ideal. So, it is not isentropic. So, from 1 we will have the exit condition after expansion in the turbine at 3. Now, 3 to 4, that will be the condensation process within the condenser, and we have assumed this process to be ideal. There is no pressure loss and it is taking place as it is taking place at a constant pressure. So, the temperature is also constant. From there, the working fluid comes out as liquid condensate, and that is the state number 4. From 4, its pressure has to be increased with the help of a pump. Ideally, the process could have been 4 to 5. 5 could have been the exit point from the pump due to isentropic compression or isentropic pressure rise, but in actual practice there will be irreversibility. So, we will get the exit point at 6, and this dotted line 4 to 6, that will denote the non-ideal or non-isentropic compression process. Then there is heat addition. From 6, heat addition will start. Initially the liquid will go to the saturation condition, then evaporation will take place, and then superheating will take place. Now, what is happening here? There is a pressure loss, and that pressure loss, due to that the actual pressure is 15 megapascal, but the pressure at the outlet of the pump could have been slightly more, and that we will see by calculation, by the given information of the problem and by calculation how we can get. So, that pressure is 15.8 megapascal. So, it indicates or it signifies that from 4 the pressure of the working fluid should be raised to 15.8 megapascal, but while passing through the pipeline and boiler tubes etc., there will be pressure loss. So, ultimately when we will supply the steam to the turbine, its pressure is 15 megapascal, and of course, it will be supplied at superheated condition. So, 1 will give the pressure and temperature condition of the steam. So, now this is the cycle. So, farm lines indicate the ideal processes, and the dotted line that indicates the real processes or processes with irreversibility. So, let us go to the next slide. So, here in the tabular form, for different state points, there are how many state points are there? Important state points 1, 2, 3, 4, 5, 6. So, for the 6th state point, we have presented the properties which are given in the problem, and at the same time which the properties which are to be calculated using the property table, in this case which is a steam table. So, for state 1, pressure 1 and temperature 1, that means pressure and temperature at state 1 is known. So, from there we can calculate the enthalpy, that is 3582 kilojoule per kg. So, this is basically your H1. At state 2, so if you remember the figure, or later on if you can go back to my previous slide of the lecture, so you can understand this is the end of expansion in the turbine if the expansion process could have been isentropic. So, what will happen? That means, whatever is the entropy at 1, that is H1, that entropy will be identical with the entropy at 2, that is S2. S2 is equal to H1. From there you will get S2 value. From there you will get the condition of the steam, and from there you can calculate the enthalpy, which is 2115 kilojoule per kg. Now, but this is not the actual condition of steam, or this is not the condition of steam at the exit of the turbine for the actual cycle. For actual cycle, what we have to do? We have to consider the isentropic efficiency of the turbine, which is eta T, and from the definition of isentropic efficiency, we can write this small equation. Pressure is known. So, eta T value is also provided in the problem. So, from there we can find out what is H3. So, that is 2335. Here what we can see, this is important to note, that this enthalpy is more than the enthalpy at point 2. Initial enthalpy is same for the both, but H3 is higher than H2. So, if the actual expansion process is from 1 to 3, then the enthalpy drop reduces. That means, the turbine does less work when we consider irreversibility in the process. So, this is very well understandable. We have done this kind of thing earlier also, but for the sake of completeness, I am giving this example once again. Now, we come to the 4. If you remember, this is the end of the condensation process or exit of condenser. So, the P4 and P2, they are same, P2, P3, P4, they are the same, and probably I remember that it is 10 kilopascal, it is given there, and it is assumed in most of the cases that the liquid which comes out of the condenser, that is saturated condition, saturated liquid. The condensate is a saturated liquid. So, we will have X4 is equal to 0, and from there we can find out what is the value of H or enthalpy, that is HF at 4 and 191.8 kilojoule per kg. Then we will have P5, P5 and P4, sorry, P5 is the pressure which we can get. The turbine pressure at the turbine exit, we know that is given in the problem, and then what is the pressure loss, that is given. So, from there we can find out what is P5, and then S5 is equal to S4 for ideal process, and then one can find out what is the condition of H at 5, that we can find out. Then this is the ideal enthalpy if the compression could have been isentropic. Now, if the compression is not isentropic and we consider the pump efficiency, which is 85% isentropic efficiency, then the enthalpy value, which is the enthalpy value at 0.6, is 211.8. So, here you see this value H5 is less than H6, and the difference between the H5 and H1 gives the ideal amount of work done, and H6 and H1 that gives the actual amount of work done, and actual amount of work done will be higher because of this irreversibility. So, this is known, and these are the points just to remind you what we have done earlier probably in our thermodynamics. Okay. So, let us go to the next slide. So, in this slide what we try to find out, there are 4 devices which are steady state steady flow devices. So, one is turbine, and next one is the condenser, next one is the pump, and next one is the boiler. For all the 4 devices, you have see we have written turbine, condenser, pump and boiler. For all these 4 devices, we want to calculate 2 quantities. One is what is heat transfer per unit mass, and what is work transfer per unit mass. Now, before that, we have to know what is the mass flow rate. We will come to this calculation, or we can do this calculation at the beginning itself, but it is better to have the mass flow rate. So, W net is equal to W dot turbine minus W dot P, that is equal to m dot, and within bracket we have got W dot turbine divided by m dot minus W dot P divided by m dot, and the work done is 100 megawatt. So, with all these things we can find out m dot is equal to 81.5 kg per second, and we can find out it also in kg per hour. If required, we can calculate what is the kg per hour. Then what we have done here, some calculation again we can see in the turbine. We are assuming there is no heat transfer because no information is given. There could be some heat transfer, but we do not have any information. Let me tell you, that is why we have put 0 here. Okay. And but there is work transfer. So, this work transfer we have found out. In the condenser there is no work transfer, but there is heat transfer, that we have found out. And then in the pump there is no heat transfer, but there is some sort of work transfer. So, that we have found out. But again, like turbine, there could be some amount of heat transfer, only we do not have the full information. So, that is why we have written it 0. But as it is an irreversible pump, there could be some amount of heat transfer. In boiler there is no work transfer. So, heat transfer we have found out from the boiler. So, how we have found out from 6 to 1, that is the process in the boiler. So, from there we have found out, and this has been written here. Now, efficiency, that is the total work done divided by what is the amount of heat supplied per unit mass. We have got the heat supplied by earlier calculation or by calculation in this particular table, that has been multiplied by the mass flow rate, and that gives 36.4% efficiency. Back work ratio is the ratio of pump work divided by turbine work. So, we have calculated all these things, and back work gives 1.6%. Again, these numbers are of interest, because you see this is very small. So, in many cases we neglect this work. Of course, here we have calculated, there is no question of neglecting, particularly if the boiler pressure is low. So, then what we can do, we can neglect this pump work, and neglecting pump work gives us little bit quick calculation of the efficiency. So, with this then we have completed our this particular example. Let us go to another example. Here what we are trying to do, we have taken the same problem, same numerical problem, but here we want to do some sort of exergy analysis. Earlier calculation, we have got the tabular form, and the tabular form gives us the value of all the important energy quantities. Here we like to do exergy analysis for all the strategic points. We want to find out the value of exergy, and also for all the devices like turbine, condenser, pump and the boiler, we want to find out what are the exergy transfer, what are the values of exergy transfer. So, this same problem, I need not read the problem, it is there, you can read it, and earlier already I have read it. So, this is again the same problem of of an irreversible simple Rankine cycle. There is no modification of the Rankine cycle, and then for a quick reference, ready reference, we can show the cycle diagram. The cycle diagram is like this. Now, if we analyze from component to component, it is like this, that the boiler gets the energy supply in the form of thermal energy. Okay. Boiler means here in the cycle what is happening, let us say the boiler process starts from 6 and it ends at 1. So, here what we get, that from 6 to 1 there is heat transfer. Okay. So, here what we can assume, that some certain amount of heat is transferred to the working fluid in the boiler. To simplify the picture, to simplify the actual picture, and then what we can find out with that heat transfer, what is the exergy associated, we can find out. So, exergy supplied to the working fluid in the boiler, we will have Q dot in multiplied by within bracket 1 minus T0 by Th. T0 is the environment temperature, and if you have read the problem, if we can go back to the problem statement once again. So, the environment or atmospheric condition was 100 kilopascal and 300 Kelvin. So, 300 Kelvin we can take to the be T0. So, here what we have got, the exergy equivalent of the heat transfer is equal to Q dot in within bracket 1 minus T0 by Th. Th is the temperature of the high temperature source. Another thing probably you have noted in the problem, but let me tell you that in the actual boiler, heat will be added at different temperatures, but here to make some sort of calculation possible, easy calculation possible, what we have done, assume the heat addition from the reservoir take place at 1500 Kelvin, as if the heat addition in the boiler takes place at some sort of average temperature, and that average temperature is 1500 Kelvin. And the heat rejection that also takes place to a reservoir which is at 310 Kelvin. So, basically the actual cycle, we are again trying to idealize it. We are doing it like this, that there is some sort of ideal high temperature reservoir which is replacing the boiler, or which is replacing the actual process in the boiler, and it is transferring heat at a constant average temperature of 1500 Kelvin. And similarly, there is a low temperature reservoir to which heat is rejected by the cycle, and that heat rejection takes place at 310 Kelvin. So, these two idealization has been made, so that we can make some simple calculation, and from there we can derive certain important conclusions. So, let me go back. So, this is the cycle, and then exergy supplied to the working fluid in the boiler, we can find out that this is the actual amount of heat supplied, which we have calculated in our previous problem. A few slides before, maybe one or two slides before, we have given this value by calculation of enthalpy. That means it is simply we got H1 minus H6 from that and then that gives you per kg of mass how much heat is supplied, but that heat is not equivalent to exergy. So, with this formula we have converted that supplied heat into supplied exergy. So, this is the exergy which is supplied, and this exergy supplied is lesser compared to the energy supplied or thermal energy supplied. So, I mean these are the point to be noted when we are we have taken up a problem like this, an example like this. Then this is the energy supplied from some external source to the working fluid. But does the working fluid or is the working fluid capable of absorbing or taking off the entire exergy supplied? So, that is one question, and let us try to answer that question. Let us try to find the answer to this question. So, exergy gained by the working fluid, that also we have got formula, we can find out from there. So, exergy gain from the gain by the fluid, we will get, this is the exit exergy which will be higher, and this is the inlet exergy. Here let me remind you, H with a superscript 0 it is coming, this is not enthalpy as such, this I have called as methalpy. Methalpy is the combination or is the summation of enthalpy, potential energy per unit mass and kinetic energy per unit mass. Of course, in this particular example, we do not have any change in kinetic energy and in potential energy, those are neglected. So, H basically denote the enthalpy in this particular case, but when I have represented it by this symbol, it is nothing but methalpy, which constitutes enthalpy, kinetic energy and potential energy. So, this is the formula, and T0 is the environmental temperature, which is 300 Kelvin. So, with this we have done the calculation, and the enthalpy exergy which is gained by the working fluid, that is 127.5 megawatt. So, you see per unit working fluid, no, this is the total exergy supplied to the working fluid is 219.76 megawatt, but exergy gained by the fluid is, or exergy absorbed by the fluid is 127.5 megawatt, 209.76 and 127.5. So, we can see that lot of exergy destruction is there. So, let me tell you one thing, actually boiler is one component in a thermal power plant where there is a good amount of exergy destruction. Okay. So, this is an example where we can see this, though we have not considered actual process of actual combustion etc., but even then the exergy destruction from the given data, exergy destruction in the boiler is very clear, and this is probably one can remember or one can appreciate. All right. So, next what we do, exergy destroyed during heat addition, or in the boiler how much exergy is destroyed. So, you see 92.26 megawatt is destroyed, whereas only 127.5 is taken off by the fluid. Then exergy delivered to the turbine to the working fluid. So, this also we can find out that we know what is the inlet condition from that inlet exergy and what is the exit exergy. So, that is the working fluid is giving this exergy, the difference is the exergy given by the working fluid in the turbine. So, this is 118.7 megawatt. So, exergy delivered by the turbine to the shaft is 101.6 megawatt. the power of the turbine, the power of the plant is 100 megawatt if you remember, but it is more because it also includes the pump work. Pump work is supplied from the turbine itself. So, this is the work, net work done by not network, the work done by the turbine, whereas Exergy delivered to the turbine is 118.7 megawatt. So, Exergy destroyed in the turbine we can get, which is 17.1 megawatt. So, at different places we can see the decrease in Exergy, okay, and then Exergy lost by the steam to the condenser or in the condenser. So, again we can use the flow Exergy formula, flow Exergy function we can use, and using that we can get 10.18 megawatt. Now, one can make a balance also. The total Exergy which is, or the Exergy which is supplied, that is supplied in the turbine, in the boiler. If I go to the previous slide, here we have got, this is the Exergy supplied, and from there we have got different kind of Exergy destruction in different component, and then we have also got the Exergy which has been converted into shaft work, that we can get. So, some sort of Exergy balance we can get, and this is left to you, you can find out this. So, this is a very interesting example how second law can be applied, how Exergy balance can be applied for a power plant. And also from here we can get where the Exergy destructions are taking place. So, as far as energy conservation and waste heat recovery is concerned, so those points one has to focus, and from there either by cycle modification or by some other means, whether we can recover some of the Exergy, and that will ultimately give us energy conservation and recovery of energy which is being wasted. All right. Now, let us proceed little bit. We can now define different kind of efficiency. We can define the first law efficiency, which we have already calculated. I think 36% or something we have got. First law efficiency of the cycle already done in the previous example. Eta 1, of course, we could have written eta, but just to demarcate it from second law efficiency, I have written eta 1. Eta 1 is W cycle by Q boiler. So, whatever W cycle means, what is the net work we are getting from the cycle, and what is the heat supplied in the boiler. So, I have not given the value, you can calculate the value. You can calculate the value as well. Exergetic efficiency of the cycle. So, this is W dot cycle divided by Exergy supplied to the boiler. Again we have calculated the same thing, and we can get the second law efficiency. Now, what do you think? Which one will be larger, first law efficiency or second law efficiency? So, you see W dot cycle is common for both the cases, but Q dot boiler is higher compared to the Exergy supplied to the boiler. So, you can make some sort of judgment which one is higher, and you can also think yourself why the two efficiencies there is a difference. And then we have idealized the cycle that as if heat is being transferred from a constant temperature source at 1500 K and heat is being rejected to another low temperature source sink, that is at 300 K. So, if we assume that for this idealized cycle we can have the Carnot efficiency 1 minus T cold by T boiler, or 1 minus T condenser by T boiler, and then putting the values of temperature we can find out this efficiency. So, this is an exercise left to you, have the three values of efficiency and try to see that why these differences are there and what you can tell from this, what you can tell regarding the cycle from these differences, and what you can also make some sort of a conclusion regarding the energy which is wastage during this cycle. Some of it is recoverable and some of it is not recoverable. That also you may think. So, this brings us to an end to the end of our discussion regarding the steam power cycle. But before closing, what I try to do, what I like to do, which is not very essential for this course, but it is essential or it is very important in general for any thermal engineer or any engineer working in the field to have a good idea regarding the steam power cycle. So, I like to show one animated small animated film on steam cycle, and this is here. So, now the animation is not working. Now, I start the animation. So, before starting the animation, let me tell you the cycle starts from here. Here we are having the coal bunkers, etc. So, here we will storage of coal. So, the coal will go through different processing and ultimately it will be crushed into pulverized coal. Along with air, it will be injected to the boiler, and some extra air will also come. We will see when the animation runs. So, here this is the furnace portion of the boiler. So, here the flame etc. we will find, and at the side we have got the tubes. So, and this is the steam drum, boiler drum or steam drum. So, here in the boiler drum we will have saturated production of some or generation of saturated steam. So, the wall of the boiler that will be utilized for generating the saturated steam. After that we will find that there is superheater. From the superheated steam will come, it will go to different stages of turbine. We will have low pressure turbine, we will have intermediate pressure turbine, and we will have high pressure turbine, intermediate pressure turbine and low pressure turbine. Okay. So, there will be also reheater, we will find out, and then from the turbine it will come to the condenser, and then it will go to the feed pump and the water cycle will be completed. For air cycle, the flue gas that will pass through different superheaters, reheater etc. Then there is economizer and air preheater. Here we can see the air heater, and then ultimately it will go to through the ESP and to the chimney. So, let me now run it. It has started running. You can see that coal is going, coal is moving, and then here you can see these are operative now, and there is some sort of a mill which is crushing the coal. This is ball mill, and then it is going to, it will be injected to the boiler. Okay. So, at one point of time it will be injected to the boiler. You have to now you see the another fan, it has started working. So, this is a forced draft fan we can see, and here we can have some sort of induced draft fan. So, basically big power plant that will be on combined draft or balanced draft, both induced draft and forced draft fan will be there. And then after some time you can find out that now combustion is taking place in the furnace zone of the boiler. And obviously, once combustion is there, there will be smoke coming out of the chimney. But now slowly the water circuit will start operating. Now, the water circuit will start operating. You can see one by one these superheaters will start being operative. Just be little bit patient, and then you can find it. So, we can see there is some sort of primary superheater, economizer, then there is another kind of a superheater, and then there will be reheaters in between, and then the steam is now going to the high pressure turbine. So, first it has gone to the high pressure turbine. So, then it will go to the intermediate pressure turbine, which is there in between, and then there is low pressure turbine. So, it has gone to the reheater. So, now it will go to the intermediate pressure turbine. Here it is going to the intermediate pressure turbine. Now, it is going to the low pressure turbine, and from the low pressure turbine the steam will come to the condenser and it will condense. So, water circuit is complete, and then there is some sort of alternator, and then there is a generator, etc. So, electricity will be generated. So, with this we are getting the water circuit and the steam circuit and also the air flow path. So, this is just an additional information. This is not essential for your waste heat recovery class, but this is an additional information we like to give you regarding this steam power plant. Thank you, and then we will go to other power cycle in our next class. Thank you.